205, 216, Signals and Systems, lecture number 24. Today is Sunday, 30th of March, 2024. The time is 10:30 in the morning. So last time, let's talk a little bit about last time. In the last lecture, we began Fourier series, Fourier transforms. We have a signal xt, a signal not necessarily a periodic. It could be any signal. Okay, when we talked about Fourier series, we restricted ourselves to just only periodic signals. But when we talk about Fourier transforms, the signals do not have to be periodic. It could be any signal, any practical signal. All right, so x is a signal. The Fourier transform of xt, well, notice that this is a time domain. The reason why I say that this is a time domain signal is because it varies. Its value depends on the variable t, which is the time variable. The Fourier transform will transform a time domain signal into a frequency domain signal. So the definition of the Fourier transform is that x of omega is the Fourier transform of xt, and its value of x omega is equal to the integral from negative infinity to infinity x of t e to the minus j omega t dt. Now, the value of this integral will not depend on the variable t because we have already integrated it out. And after we've integrated it, we only have the variable omega that comes out. So the value of the integral will be a function of omega. That's why we denote it by x of omega. So this is the frequency domain signal. Its value depends on the frequency omega. Omega is a frequency. Okay, omega is the angular frequency, and it is equal to 2 pi times the ordinary frequency f. The unit of omega is in radians per second. Now we were able to evaluate the Fourier transform of a couple of signals. The first signal to mention is the unit impulse. We had the unit impulse. The Fourier transform of the unit impulse was shown to be just one. It's a constant. Second signal of interest was the complex exponential. And for the complex exponential, we knew it was equal to the transform of a complex exponential is in the form of a delta function, and delta at the frequency omega 0. So this is the complex exponential at frequency omega 0, and in the frequency domain, the signal has only one value, and that value is at omega 0. The third signal that we were able to to obtain last time was the rectangular signal. If you recall, a rectangular signal is like a square pulse signal, rectangular. T over capital T is a signal that is constant over a certain time interval. Yeah. So it goes from minus t over 2 to t over 2. The width of this is t, obviously, and the height is 1. And its Fourier transform is equal to t sinc function of omega t over 2. So these are basic signals that we were able to obtain their Fourier transforms. Now, in general, x of omega will be a complex valued function. When I say a complex valued function, I mean that its value at any omega could be a complex number. So that's what I mean by a complex valued function. But if t is a real number, so because it is a complex valued function, it has both magnitude and a phase. So the magnitude is denoted by the absolute value of x of omega, and the phase is denoted by this notation, this symbol. Okay. Also, we talked about some of the important properties of the Fourier transform. The first one was that if t is a real valued function, then its value conjugate will be equal to, actually I should say this, x of minus omega will be equal to x of omega conjugate. Let me check that. Yeah. Okay, so this means that the magnitude is an even function. So this means that the magnitude is an even function, and the phase is an odd function. Okay. The second property that we talked about last time was linearity. So the Fourier transform of a x of t plus b y of t is a x of omega plus b y of omega. Okay, so this means that if we want to take the Fourier transform of a linear combination of two signals, then the result will be the same linear combination of the Fourier transform of those two signals. So that's the linearity property. This is called the linearity property. And the third property was about time shift and time scale. Time shift signal. A time shift signal x of t minus t0, we're shifting signal x by time t0. And if you take the Fourier transform of it, the result will be the Fourier transform of x e to the minus j omega t0. So that's a time shift property. Okay. The fourth property is the duality. The duality states that if xt has the Fourier transform pair of x omega, then suppose we have this. Then capital X of t will have the Fourier transform of 2 pi x little x of minus omega. So basically, we are bringing the two functions at the top down across to the left and to the right. Okay, that is duality here. Yeah, that is duality. We also had a couple more properties, and those were time scale and time transformation. Where was that? Yeah, I was here. We have run out of space. Another property is called the time scale. If we're doing the time scale of x by a factor of a, the result we're taking the transform of x of at. The result will be 1 over absolute a x of omega over a. Okay, let me check that. Here, all right. And the other one was time transformation. Okay, let me bring it down. Tell you the truth, I don't particularly remember the formula for time transformation because I don't use it very much. I don't use it very often. So x of at minus t0 has a Fourier transform pair of 1 over absolute a x of omega over a e to the minus j omega over A times T0. So that is time transformation. All right. Now, I would like to stress. What's that? Oh, WebEx is updating. That's frustrating. Mm. Now everybody. So it's just me now. Everybody's gone. WebEx up was updating. That's annoying and frustrating. It shouldn't happen. Uh, what is going on? Uh, okay. Now it's just me. All right. I would like to go on, continue, and this is called time multiplication or modulation. It states that the Fourier transform of the product of two signals is equal to the convolution. Oh, by the way, another one, almost forgot. The next one is kind of important, and that is the convolution. If I'm doing a convolution integral between two signals, x and y, and take the Fourier transform, the result would be the product of their Fourier transform. So this is a time convolution property. Now, the next property I'd like to talk about is called time multiplication. So we have two signals multiplied together, and if you take the Fourier transform of the product of two time signals, the result would be the convolution between their Fourier transforms with the factor of 1 over 2 pi at front. Okay, so for example, we know that a cosine of omega 0 t has a Fourier transform pair of pi and delta at omega 0 plus delta at minus omega 0. Okay, and the rectangular of which t has Fourier transform pair of t sinc function omega t over 2. So from time multiplication, it follows that if we multiply these two together and take the Fourier transform, so Fourier transform of rectangular t over capital T cosine of omega 0 t and take Fourier transform, then the result would be 1 over 2 pi. 1 over 2 pi, and I'm gonna bring pi t out, and sinc of omega t over 2 convolved with delta omega minus omega 0 plus delta omega plus omega 0. Now, from linearity of convolution, I could bring the sinc function to convolve with each of the deltas. So this is going to be t over 2 sinc of omega t over 2 convolved with delta omega minus omega 0 plus sinc of omega t over 2 convolved with delta omega plus omega 0. Now, we know from chapter 2 that if these two guys are convolved together, then the result would just be the sinc function shifted by this value. So the first convolution gives us sinc of omega minus omega 0 t over 2. That is the sinc function shifted by omega 0. Okay, and the second convolution gives us sinc of omega plus omega 0 t over 2. That's for the second convolution. Now, if we plot the graphs of these two signals in the time domain signal, for the time domain signal, the graph would be like we have rectangular of width t. The inside of this rectangular is a cosine function. So it is a cosine function that extends from minus t over 2 to t over 2. So the purple signal is a cosine at frequency omega 0. So this is rectangular t over t cosine of omega 0 t. The oscillation inside has a frequency of omega 0. Okay, and this is the time domain signal. This is the X signal. Now, the Fourier transform of it, which is the frequency signal, is basically sinc functions, basically two sinc functions, one at omega 0 and the other at minus omega 0. So this is minus omega 0 and this is omega 0. So we're going to have to draw two sinc functions there. So it will be this and this. Okay, so this guy is, oh, I'm sorry, this guy is this one, and this guy is this one. So there are two sinc functions, and the height, the maximum height of the sinc function is t over 2, capital T over 2, and the zero crossing, of course, is determined by this one. Zero crossing would be 2 pi over t. I'm sorry, the width. This would be minus omega 0 minus 2 pi over t, and this would be minus omega 0 plus 2 pi over t. This is omega 0 minus 2 pi over t. This is omega 0 plus 2 pi over t. So those are the zero crossings. Okay? And that is time multiplication. Another one is called frequency shift. If we multiply a time domain signal x by a complex exponential e to the j omega 0 t, its frequency domain signal, its Fourier transform would be the Fourier transform of x shifted to the right by omega 0. If omega 0 is negative, then it will be shifted to the left. Okay, so that is frequency shift. So multiplication by a complex exponential means that we are actually performing a frequency shifting of its frequency spectrum. The frequency spectrum will be shifted by this amount, omega 0. Now let's do another example. This example is called modulation. A modulation is a process of shifting the frequency of a time domain signal. Well, we do that by multiplying the time domain signal by a sinusoidal signal at frequency omega 0. Okay. The problem about this property is that in practice, we don't have complex exponential signals because this one is a complex valued signal. But in practice, we only have cosine and sine signals, sinusoidal signals. So basically, actually, the complex exponential is essentially a sinusoidal signal in practice. So that's why we are multiplying by cosine signal. Now, to study what the Fourier transform of y is, we are going to use Euler's identity, okay, to write this sinusoidal signal as a form of complex exponential signal. So from Euler's identity, okay, we have cosine of omega 0 t equal to e to the j omega 0 t plus e to the minus j omega 0 t over 2. So it means that we can write y as 1/2 x of t e to the j omega 0 t plus 1/2 x of t e to the minus j omega 0 t. So the Fourier transform of y, which is y omega, would be by the linearity. We have 1/2 of Fourier transform of x of t e to the j omega 0 t plus 1/2 the Fourier transform of x of t e to the minus j omega 0 t. Now, from frequency shift, the first one would be 1/2 x of omega minus omega 0, and the other one is 1/2 x of omega plus omega 0, or 1/2 of x omega minus omega 0 plus x omega plus omega 0. So in other words, for example, if our signal x has a spectrum of that looks like this, if our signal x has spectrum that looks like a triangle here, so suppose this is the spectrum of x. Now, if we multiply x by cosine at frequency omega 0, then the spectrum of y will be the spectrum of x shifted to the right and to the left by omega 0 with amplitude, with half of amplitude. So it would be this. Well, let me mark those frequency down. So it would be this. So this is the spectrum of y. Now, this would be a over 2. Okay, and this would be minus omega 0 plus b, minus omega 0 minus b. This is omega 0 minus b. This is omega 0 plus b. All right, so this is called modulation. Modulation is a process that would shift the frequency spectrum of our signal to our desired frequency. Okay, in this case, the desired frequency is omega 0. It's kind of like it is translating our signal to those frequencies. Okay. The next property is the time differentiation. If we differentiate the signal x with respect to time, then essentially in the frequency domain we are multiplying the Fourier transform of x by j omega. So every time we differentiate the signal with respect to time, then we are essentially multiplying the frequency domain signal by j omega. Okay, so this is called time differentiation. Example, suppose we want to find the Fourier transform of the signum signal. The signum signal is defined as 1 when times positive and -1 when times negative. So the graph of a signum signal would look like this. Let me bring this one up a little bit so that you don't get confused. So the signum signal here is 1 when times positive and -1 when times negative. Okay, this is the signal 1 and -1, 0 here. Now we want to find the Fourier transform of this one. The Fourier transform of this one is not straightforward. It's quite tricky. We have to use some of the tricks. Okay, we cannot use the definition of the Fourier transform directly on this one because there is a discontinuity at time 0. So instead we're gonna write xt as 2u minus 1. Okay, so we notice that so let x be the signal. Okay, so we notice that x of t is 2ut minus 1. Now, why is that so? Because you see the height of the signal is 2, right? It jumps from -1 to 1, so it jumps 2 units up. So that's why we have 2ut at 0. It jumps at 0, so 2ut. But then, if it was 2ut, then we would have from 0 to 2, right? But in reality, we are having from -1 to 1, so we have to bring 2ut 1 unit down. So 2ut is this, right? After we've brought it down, we're going to have this. So that's why we have 2ut minus 1. Now, if we take the first derivative of xt with respect to time, then we're going to have 2 du by dt minus d1 by dt. But d1 by dt is 0 because 1 is a constant. And du by dt is delta, as we already know. So that is 2 delta t. And then we take the Fourier transform of both sides. On the left-hand side, I have d by dt of xt, right? And on the right-hand side, I have 2 Fourier transform of delta. But we know the Fourier transform of delta is 1, so the right-hand side is 2. While if we use the time differentiation here, we know that the left-hand side is j omega x of omega. So we can conclude that x of omega is equal to 2 over j omega. And this is the Fourier transform of the signal. You see, it is not a real valued function because the signal is an odd valued function. It's an odd function here. This is an odd function. So it has only the imaginary part. It doesn't have any real part at all. Okay. But we could plot the magnitude and the phase. Now the magnitude of x is just 2 over omega, and this is the graph of it. It is a hyperbola graph, 2 over omega. So this is 2 over absolute omega, actually. 2 over absolute omega. And the phase, okay, the phase of x would be, when omega is negative, it would be pi over 2. When omega is positive, it would be minus pi over 2. Because the j is in the denominator, right? So if omega is positive, so it's equal to 2 over j, right? And the phase would be minus pi over 2. But if omega is negative, it would be minus 1 over j. And so we bring j up to the top, we're going to get j, right? And the phase would be pi over 2 when omega is positive. Minus pi over 2, actually. Sorry. Okay. The next example is about triangular pulse. No one is here, only me. The triangular pulse is this. Okay, let's plot it. Actually, we've done this already, if you remember, in the convolution property. So let's plot, but we're going to do it again. Okay, there are two ways at least to find the Fourier transform of this rectangular pulse. So if we plot it, 3RI t over capital T, okay, we would have a rectangle, a triangle actually, no, triangle, yeah. The left extends to negative t, the right extends to positive t, and the height is 1. So this is defined as the triangular pulse. We have actually done this already, if you remember. Let me see. Here, this is from last time. Okay, this is from last time. We actually have done this one using convolution property, using the time convolution property. Okay. I'm gonna paste it here. This one is using the time convolution property. Now, instead of time convolution property, we're going to use differentiation property. Okay, so here we have this one, right? We have this one. And then this is another method. Okay, this is another approach in finding this guy. Okay, I would like to stress again, I would like to say again that this result is by using time convolution property, but now instead of time convolution property, I'm going to use differentiation property to find this one, and you'll see that they will exactly match. The result will be identical to each other. So to do that, we're going to define x as this triangular pulse, and then we differentiate x with respect to time. Now, if we differentiate this graph, it would be the slope, right? And the slope is 1 over t. So it's 1 over t here. And the slope, this graph extends from minus t to 0. That's why I have rectangular pulse here. And if I differentiate this portion of the graph, the slope will be negative. So negative 1 over t. So negative 1 over t, and extends from 0 to t. That's why we have rectangular pulse here. Okay, and then so this guy would be here and here. The slopes are this. Okay, and then we take the Fourier transform of both sides. On the left hand side, this is the Fourier transform of the derivative of x with respect to time. So it is j omega x. And on the right hand side, this is just the Fourier transform of the rectangular shifted in time. And the time shifted, the amount of time that we are shifting it is minus capital T over 2. So we are multiplying in the frequency domain by e to the j omega t over 2 by shifting time shift property. And the other one, again, it is a time shift property, so we multiply it by this. Okay, actually, the time shift property This is the time shift property. Here, this is the time shift property. So I think I have to multiply it by minus. That is a negative symbol here. Okay, and then you see the Fourier transform of rectangular is sinc, so we have the same sinc signal, right? So we bring the sinc signal out, and the inside would be just e to the j omega t over 2 minus e to the minus omega j over 2, j omega t over 2. And that converts to the sine signal. Okay, so this, to go from here to here, we use sine of, we use Euler again, e to the j omega t over 2 minus e to the minus j omega t over 2 is equal to j2 sine omega t over 2. So that's why we have this one. Okay, and then to go from here to here, I'm just multiply I'll bring j omega down across to the right, right? So I have x of omega equal to j2 over j omega sine of omega t over 2 and sinc of omega t over 2. And then the j's would cancel, all right? And then I multiply by t, and over omega t over 2, right? T sine omega t over 2 divided by omega t over 2 and sinc omega t over 2. But then I notice that this is just sinc function, right? So I have t sinc omega t over 2 times sinc omega t over 2. And then I have t sinc squared omega t over 2 here, right here. And the result you see exactly matches the one that we had from the previous lecture. So these two different approaches gives us the same result. Okay, so either we use a time convolution property to find this Fourier transform, or we use differentiation property to find this Fourier transform. Either method will give us the same result. All right. The next property is called time integration. Okay, we are integrating x of x, okay, from minus infinity to t, and the result would be this one, right? And the next one is called frequency differentiation. If we multiply, well, actually, for a transform of t, x of t is j times the derivative of x with respect to omega. Here, this is the first. This is the one. Actually, well, this is time. This is multiplication by time. Okay. Yeah. Okay. This is frequency differentiation. So this is the summary of the properties of Fourier transforms. The ones that are important are linearity, time shift, duality, frequency shift, convolution, and differentiation. So these are very important. You have to be able to, you have to understand those. And the rest is just for completeness. Okay? All right. Now, we will talk about, well, actually, we will talk about frequency response of LTI systems. Actually, sorry. Frequency response of LTI systems. Now, from chapter 2, if we have an LTI system characterized by this impulse response, okay, and X as the input, then the output will be the time convolution between X of t, the input, and the impulse response H. So if we take the Fourier transform of both sides, okay, we're gonna have X of omega, we're gonna have Fourier transform of H as H of omega, and we're gonna have Fourier transform of Y as Y omega. But now we know that the Fourier transform of convolution is just the product of the Fourier transforms. So Y of omega would be X of omega times H of omega here. So this is a very important equation, okay? And that is the name for this function. This function is called the frequency response of the LTI system. It is defined as the Fourier transform of the impulse response of that system. Okay? Here. So there are two ways to determine if you're given a system, a linear time invariant system. There are two ways to determine the transfer. I'm sorry. There are two ways to determine the frequency response of an LTI system. Either you find the Fourier transform of its impulse response, or you use this equation. If you know the output as well as the input, then you will be able to find the frequency response using this equation. But if you don't know y and x, but instead you know the impulse response, then you could also find the frequency response by taking the Fourier transform of the impulse response. So there are two ways to find the frequency response, either using this equation or using this equation. Okay. Now, generally, h of omega will be a complex valued signal. So there, it is described by two functions. First, by the magnitude response. Second, by the phase response. Okay. So if you take the magnitude of this signal, then you see that the magnitude of the output would be the magnitude response of the system multiplied by the magnitude of the spectrum of the input. On the other hand, the phase response of the system would be the phase of the phase of the output would be the phase response plus the phase of the input. Okay? All right. Now, from this equation, you see that the magnitude of the output signal would be dictated, would be controlled by the magnitude of the magnitude response. That's why we call it magnitude response. For example, if at certain frequencies this guy is very small, then it means that the system will try to attenuate the value, the magnitude of the input, okay, by multiplying by something very small. But if at some certain frequencies this guy is very large, then it means that that system will kind of like amplify the components of the input at those frequencies. So depending on the value of the magnitude response at the frequencies that we're interested in, the system will either amplify or attenuate the magnitude of the input at those frequencies. That's why we call it magnitude response of the system. Okay? So in choosing an LTI system with the right frequency response, we can choose the frequencies of the input signal to be present or absent at the output. Such a system is called a filter. Okay? For example, if some frequencies h of omega is 0, then those frequencies from the input will not be present at the output. Okay, so that's we're shutting down the input at those frequencies. For example, if an LTI system has the frequency response that looks like this, if the frequency response looks like this, then if the input is this, then if you multiply them together, the result would be the spectrum of the output, right? And the spectrum of the output would be the spectrum of the input, but filtered out after B. So it looks like a house. Oh, here. This would be the spectrum of the output. You see, the input with frequencies above B and below negative B will be filtered out. Filtered out means it will be multiplied by 0. Okay, so you get 0 out at those frequencies. So you get 0 out at those frequencies. But frequencies between minus B to B will be multiplied by 1. Okay, the value of the input at those frequencies between minus B to B will be multiplied by 1. So those frequencies will not be affected by the system. So they will come out to the output. Okay, but beyond those, above B, the input cannot come out. Okay, this process is called filtering the signal. Okay, the LTI system here is called the filter. It allows lower frequencies to come out while rejecting higher frequencies. So this system allows lower frequencies low frequencies from 0 to be present at the output while shutting down while rejecting frequencies beyond be from passing through to the output. We call this low pass filter. This is an example of an low pass filter. Low pass filters mean that low frequencies are able to pass through. That's why we call it low pass filter, while higher frequencies will not be able to pass through. So this means low pass filter means input frequencies low frequencies are able to pass through. Okay, that's why we call it a low pass filter. See here, lower frequencies are able to pass through and present at the output, right? While higher frequencies are not able to pass through, they will be absent from the output at the output. So there are a lot of filters. Okay, the first one we talked about is a low pass filter, or call it LTF. Is an LTI system that attenuates the magnitude of the input signal in the high frequency range, starting from a particular frequency to infinity, while trying to pass through the input signal in the lower frequency range, starting from 0 to that particular frequency. Another one is called the high pass filter. The name suggests differently. Okay, so as the name suggests, high pass filter will allow input signals at higher frequencies to pass through, while attenuates the input signal at lower frequencies. Band pass filter means that it passes through input signals that is in between a band of frequencies range. Okay, starting from some value until some value. Okay, so another one is called band stop filter. Band stop filter is a contrary to the band pass filter. While band pass filter allows certain frequency range to pass through, band stop filter will reject certain frequency range from passing through. So if we plot the graph of the frequency response of each type of the filter, there are four, right? There are four. There are four. If the frequency response looks like this, you see, at lower frequency, it passes through better than at higher frequencies. So this is the frequency response of a low pass filter. But if the response looks like this, you see, it passes through high frequencies while attenuates lower frequencies. So this is the graph of a high pass filter. Now, as for the band pass filter, the graph will look like this. This is a band pass filter. Okay, band pass filter. passes through certain range of frequencies. Okay, and the band reject filter will be the opposite to the band pass filter. This is band reject filter, band stop filter, sorry, band stop filter. Okay, so now another one is called the ideal low pass filter. You see low pass filter here attenuates nicely, right? But in the ideal case, in the low frequencies, we want the filter to pass through entirely, okay? While in a high frequency, we want the filter to shut it down entirely. So the ideal filter, the magnitude response of an ideal filter will look like this. This is for the ideal filter. It will pass through entirely without attenuation and shut down entirely in the higher frequency. So this is the magnitude response of an ideal filter. This is omega c. This is minus omega c. Okay, and the frequency response is given by this complex exponential function. The parameter t0 means that the filter may delay the output by certain amount of time. Okay, it is not perfect. It may delay the input by t0. If t0 is 0, if this guy 0 means that the filter doesn't delay the input at all. But sometimes the filter does delay the input by the time t0. So we might have this complex exponential, because we know from time delay, right? Time delay property of Fourier transform. If we delay the time domain signal, it means that we are multiplying the frequency domain signal by the complex exponential like this. Okay, and this is the ideal high pass filter frequency response. We may want to plot this one. The graph will look like this. Okay, this is omega c, this is minus omega c. Again, it may delay the input by time t0, so we have this one. And for ideal band pass filter, the graph will look like this. Oh. This is the graph for an ideal band pass filter. Okay, and omega c1, oops, sorry, omega c1, omega c2, minus omega c1, minus omega c2. As for the band stop filter, it is the opposite of the band pass filter. So omega c1, omega c2, minus omega c1, minus omega c2. I have to put some absolute value here, absolute value here. Okay. All right. Now you see the difference between this graph and this graph, right? For example, for the low pass filter, this is in practice. okay, it will not shut down completely, nor it will pass through completely. All right, there are some non-ideals present in the low pass filter, but for ideal case, when we say passing through, it means that it passes through completely. But if we say filtered out, it will be filtering out completely without anything passing through. So this is the ideal case. Ideal. This is not ideal in practice. In practice, we will not have ideal case. We will not be able to construct this. We will only be able to construct these filters. But nevertheless, ideal cases are easier to do some analysis. So in this course, we will be only interested in ideal cases. All right. Okay, I'm gonna leave these examples for the next time then, because apparently there are no people here. So I'm talking alone. All right, bye bye. Okay.